Okay. Now, alkenes, right, are highly reactive due to the presence of your pi bonds. The yellow and green areas of this particular molecule, they are all flat because the carbon atoms are sp2 hybridized. So they are all trigonal planar. This purple color pi bond is perpendicular to the plane. And therefore, the purple color area that you're looking at on page number 17, right, is exposed to the external surroundings. Who will be very attracted to electron-rich areas? Obviously, we call them electron-deficient species. And electron-deficient species are known as electrophiles. Alright, clear on this? Okay, now we go back to our chapter itself. Are called electrophiles, alright? So the greater chemical reactivity is due to the presence of the carbon-carbon double bond and the loosely held pi electrons. Provide an electron-rich area where it is highly susceptible to incoming electrophiles, understand? Or what we call as electron-deficient species. Alright, I'm not going to go through nomenclature, guys, which is naming. I'm not going to bother about that. But what I'm going to do is exercise number 7 as a recap, okay, of the previous lesson. Okay, so if you take a look at exercise number 7, they're asking you how many stereoisomers can the following molecules exhibit. Alright, now if you take a look at this molecule over here, can you all please write down how many stereoisomers? Stereoisomers are cis trans, EZ, and enantiomerism. Okay, one of the three: cis trans, EZ, and enantiomerism. So when someone asks you how many stereoisomers, this is one of the three. Are you all clear? Okay, so we're going to start off with enantiomerism, which is to find chiral centers, guys. So what are chiral centers? sp3 carbon bonded to 4 different groups. So if you notice, the one that I circled in purple, these are your sp3 carbons. Unfortunately, your sp3 carbons are bonded to the same group. So there are no chiral centers in this molecule. So in terms of enantiomerism, don't have. Now, if you all recall, cis-trans isomers, there are 2 criteria. The first criteria is what? Across, on each doubly bonded carbon atom, there must be 2 differing groups. Criteria 1. Second criteria, across the carbon-carbon double bond, there must be similar groups. Across carbon-carbon double bond, similar groups. So therefore, there's cis-trans isomer here. Understand?
Wait, what's the first criteria?
Each doubly bonded carbon atom must have 2 different groups. HCH3, 2 different groups, right? Correct?
Yeah.
CH3 and this whole group here. These 2 different groups. Now we move on to the next carbon-carbon double bond. When we move to the next carbon-carbon double bond, guys, I do hope that you all are able to tell that this carbon-carbon double bond will not have cis-trans isomerism. And why is that so? Take a look at the first criteria. Each doubly bonded carbon atom has the same groups. So we cannot do cis-trans isomerism.
So they must have different groups.
They must have different groups on each doubly bonded carbon, and across the carbon-carbon double bond must have similar groups. If you want cis-trans. If you want EZ, you just need to meet one criteria, which is differing groups on each doubly bonded carbon atom. Okay? So as you can see over here, guys, there's only one area where you can have cis-trans isomer. This one cannot. So therefore, the number of stereoisomers is 2 because you're either in cis or trans. Agree? Now the answer key is on the next page if you think that my working is very dirty. Now, as you can see, this is called a diene, guys. A diene is an alkene molecule. Agree? So, what I want you guys to take home after this lesson is, please make sure that you need to know that just because I teach you alkenes, right, that doesn't mean that your previous chapter, which you learn free radical substitution, you forget about it. Because even in an alkene, you can undergo FRS. Can you all see now? The CH3 groups can undergo free radical substitution. Because for you to undergo free radical sub, you only need an sp3 carbon hydrogen bond. You don't need anything else. Alright, so even though this molecule is an alkene, but he still can undergo FRS. Clear? And if you recall the last lesson, you do realize that the carbon-carbon double bond here will tend to undergo addition reactions. Because it's easier to break the pi bond than break the sigma bond. Okay? So that's why I label FRS. Over here is electrophilic addition. Okay, we will explore it very soon. Now, in the last lesson as well, we also covered the reaction of propene. If you still recall propene, propene is a 3-carbon alkene. Can you see? This 3-carbon alkene, there's an sp3 carbon over here. There's also an sp2 carbon over here. So this section can undergo FRS. This section can undergo electrophilic addition. Okay? So please, guys, yes?
What's the requirement for FRS?
UV light. Alright, so if you notice, if I do put Cl2 in CCl4, also known as liquid chlorine, in the dark means absence of UV light, only EA can occur. The pi bond is broken and the 2 chlorine atoms have already been inserted. However, guys, if I put Cl2 in UV light, both the addition and the substitution reaction can occur. So what I'm trying to say is that addition of halogens is light independent. Understand? Clear? This was what was covered. So your eyes should also be very fixated about the conditions. If there's UV light, FRS and EA can both occur in the same molecule. Don't you all see UV light, you only focus on undergoing FRS. If there's a carbon-carbon double bond, that carbon-carbon double bond will also be broken. Are you all clear on this?
Mm-hmm.
Yes? Okay. Now, if you all understand, could you all move to molecule B? Okay? And then ask yourself, is there a chiral carbon? Okay, so let's start from the extreme left. Clearly, there is no chiral carbon. You all agree not? Okay,
Yes.
There's no chiral carbon. Next, we move on to cis trans. Guys, across the carbon-carbon double bond, are there two? On each doubly bonded carbon atom, are there 2 differing groups? Right? Across the carbon-carbon double bond, is there similar groups? Yes. CH3, CH3, agree not? So therefore got cis trans here. Let's move on to the next one. On each doubly bonded carbon atom, is there 2 differing groups? Yes, right? Yes or no? Yes, there are 2 differing groups. Are you able to see that? One here, one here. Agree not?
Yeah.
Okay. Hey, are you all in agreement?
Yeah.
Okay. Then after that, however, across the carbon-carbon double bond, there are no similar groups. So therefore, we cannot call him cis trans. What will you call that? If you meet one criteria but never meet the second one? EZ isomer. Alright? Clear? Okay, so therefore, because there are 2 areas, can you see that, guys? There are 2 locations where EZ and cis trans isomer can occur. There could be a total of 4 combinations. Could you all tell me why this fella cannot undergo cis trans? This one here. Because the doubly bonded carbon atom contains the same substituent, which is hydrogen. Alright, clear? So hence there are only 4 possibilities. Clear now? Think about the 4 possibilities. It could be cis, cis-trans, trans-cis, and then last one, trans-trans. That's why I got 4. Okay? And then the last one, guys. Let's look out for chiral centers first. I think in the last lesson as well, I mentioned that to find chiral centers, we just look out for the letter Y. Very good. Okay, we look out for the letter Y. Now, I immediately cross out all this. You know why not? Because these are sp2 carbons. sp2 carbons cannot give you chiral center because you need to be sp3 bonded to 4 differing groups. That's why I put X here. Now there's a second reason, listen, why I put X on the carbon-carbon double bond. Now you might be thinking, but carbon-carbon double bond can give me cis trans, right? Cis trans isomerism arises due to restricted rotation about the carbon-carbon double bond, correct or not? Because of the restricted rotation. I want you all to take a look at this. When you put a double bond in a ring, okay, there will not be restricted rotation. There will be totally no rotation at all. Because when you put the double bond in a ring, you lock him in his position. So therefore, there will not be cis, neither will there be trans. Think about it in another way. The definition of stereoisomers is same MF, molecular formula, same structural formula, correct? And the last one is, they differ in their orientation in three-dimensional space. When you put a double bond inside a ring, you've locked him in a planar position, which means that there will not be any orientation of atoms in three-dimensional space. So as a result, when you have a carbon-carbon double bond in a ring, the carbon-carbon double bond cannot even give you cis-trans isomer because they will only be in one configuration, which is a planar or a cis configuration. Understood? Because the groups will be fixed in that particular location. Do take note of that now, guys. Alright, so let's look out for the letter Y. This is one chiral center, the second chiral center, third chiral center, and the fourth chiral center. Agree? Hello?
Those have
This one, Sorry, why?
the two purple ones, right? They have a hidden H, is it?
Yes. This one, is it?
No, the purple one.
The dot.
This one, yes, of course. They won't draw CH for you. Alright, Ken? So are you able to see 4 chiral centers? So therefore 2 to the power of 4. And then how many EZ isomers? So this one here is EZ is not cis trans. You all know why, right? Because across the carbon-carbon double bond there is no same group. And then this one here got cis trans isomer, no guys? Don't have.
That's the same group.
Sorry again? Because the same group is attached to the doubly bonded carbon atom. They will ask why this got no cis trans. So you have to mention similar substituents attached to the same doubly bonded carbon atom. Alright? So 4 chiral center, 1 EZ, so 2 to the power of 5, which is 30. Okay?
I thought it was two.
You thought it was 25? Alright. And then in the last lesson as well, I covered this between cis and trans. Correct, guys? Could you all please adjust the spelling? So not the spelling, there's a typo here. Then? Okay. So just for the record, whatever that we covered in the last lesson is, in terms of melting point, trans molecule is greater than cis because of its packing ability. Because trans molecule packs a lot better than cis, so greater surface area of contact. Can? Alright, and then for boiling point, if the molecule is polar, the cis molecule will have a higher boiling point than the trans because the individual dipole moments cannot cancel out. Yeah, you're clear on this? Okay? Now, for solubility, guys, on the following page, page 43. Ready?
Wait, can you go back?
Why?
Just, oh yeah. Okay.
Why is that so? Why is it 1.6 is lower than 1?
I talked about it in the last lesson already. You go and watch the video, okay? For under stereochemistry. Can? Alright. For boiling point, it is trans lower than cis because the individual dipole moments cannot cancel out. This one is the way you pack, the packing efficiency. And when you pack very, very well, your surface area of contact will be much greater. Therefore, London dispersion forces stronger. Solubility is same as alkene. You all know why, right? Because alkenes are also non-polar. Alright? Are you all clear now?
Yes.
Yes? Okay. Shall we start on the reactions, which is the more important part of today's lesson? Okay. Now, I mentioned in the previous lesson that alkenes undergo electrophilic addition. However, this particular reaction, they don't call it electrophilic addition. And students always wonder why. So, before that, let us do a recap of why alkenes undergo electrophilic addition. Okay? Now, this is based on previous lesson. I would like you all to look at the molecule below first. Here. Come. If you look at the screen, you'll be able to see that when ethane approaches a halogen molecule, because of the fact that ethane is neither electron rich nor electron deficient, when he approaches the halogen molecule will not be polarized as much. So when they undergo a breakup, they're going to break up homolytically. What's homolytically? Which means homo in Latin means same. So each atom receives one electron. X receives one electron, the other X receives the same one electron. And because they receive the same number of electrons, we call it homolytic. Are you all clear? Okay. Having said that, our dearest alkene, when alkene, who is electron rich, I think we already covered that, approaches the halogen molecule, what it does to the halogen molecule, it polarizes it. And when it polarizes it has a delta plus as well as a delta minus, induces a dipole. When it induces a dipole, can you see the two electrons between X and X will now go towards the delta minus. What type of fission do we call this, guys? Heterolytic fission. The X atom on the left will receive 0 electrons. The X atom on the right will receive 2 electrons. So therefore, you produce X plus and X minus. You all want to commit to memory. Every time you undergo heterolytic fission, you will get an electrophile and a nucleophile. Every time you undergo homo fission, you get radicals. So now we already understood that the attacking species is either an electrophile or a nucleophile. Agree not? Alkenes undergo addition reaction. Why? Because it's easier to break the pi bond than breaking the sigma. Agree not? Than breaking the sigma bond. Are you all in agreement as well on that? So alkenes undergo addition reaction. But now the question is it electrophilic or is it nucleophilic addition? So if you are an alkene who is electron rich, will you be more attracted to the electrophile or the nucleophile? Electrophile, right? Because electrophiles are electron deficient. And hence the name of the mechanism is called electrophilic addition. Because the first step or the slowest step of the reaction involves the addition of an electrophile. Are you all clear? So now I'm going to use that same concept. The concept is the alkene molecule approaches the halogen and polarize him. Now you're going to go back up and try to explain why we cannot do this same concept with regards to hydrogen. When your alkene molecule approaches hydrogen, right, they realize that they cannot polarize the electron cloud of hydrogen. Anybody knows why? Why can't they do the same thing that they do to the halogens to hydrogen? Because H has only one electron, and the one electron is very close to the nucleus. For you to be able to polarize an electron cloud, your valence electrons must be very far away from the nucleus. That's why you can polarize. You can dictate his movement. But when your electrons are very close to the nucleus, you can't dictate his movement. So if you want hydrogen to react, hydrogen will undergo what type of fission? Homo or hetero?
Homo.
It will undergo homo. But the problem with undergoing homo is that you need UV light, right? Correct or not? You need UV light. But UV light only has a certain wavelength. You all agree? Yes? And that certain wavelength can only give rise to a certain amount of energy broken. Now, you must understand, according to table 10, to break HH is 436 kilojoules of energy, which is a lot more than UV light can master. So that's why it cannot undergo homolytic fission, even though he can break up homolytically, theoretically speaking. Understand, guys? Furthermore, if you supply 436 kilojoules just to target hydrogen, you're going to compromise the other bonds that are present in this particular alkene. The CH bonds will also be overcome as well. You all understand, no? And we do not want that to happen. And in order for us to do that, guys, we need to lower this 436 kilojoules. And how do we lower the 436 kilojoules? Is by adding a catalyst. Alright? And if you notice guys, what's the state of matter of these catalysts? Nickel, palladium or platinum? What state of matter are they in? Solid, very good. And what do you think is the state of matter of your reactants? Gas. Are they the same? Gas and solids. They are not the same. And because they're not the same, we call them heterogeneous catalysts. Because hetero in Latin means different. Clear? And what do heterogeneous catalysts do, guys? It is like a platform, right? For the reactant particles to land on. As the reactant particles land on the surface of the catalyst, it forms weak bonds, correct or not? And what happens is, the bond length starts to lengthen. Agree? And when the bond length starts to lengthen, the bond energy will start to drop. So therefore, because you're using a catalyst, and the catalyst provides a what pathway? Alternative pathway, we cannot call him the same mechanism as the rest of the reactions. Because the rest of the reactions doesn't involve what, guys? The rest of the reactions doesn't involve a heterogeneous catalyst. Clear? Okay, I think I have to reset this. Now I have to reset the app. Okay.
You watch this before?
Yeah.
What's this?
You all haven't watched this?
I watched it once, but not fully.
It's good, it's good.
What's this?
This one that scam people lah. As in not scam people. She wanted to create she wanted to be a mogul, but she didn't have any money. Yeah. Okay, anyway. So that's why, guys, we cannot call him electrophilic addition. Hey, excuse me. You all must know this. We cannot call this electrophilic addition of hydrogen. Okay, this is called reduction, or what we call as catalytic hydrogenation.
I a bit.
Okay? Can? So if I were you, I would usually choose palladium or platinum because it is at room temperature. Okay? Okay, guys, the applications of the reduction of alkenes is stated over here. Now, this is called vegetable oil to margarine. Have you all heard of this process before? You all learned this in secondary school, the industrial application of hydrogenation, yes? Yeah? Now, if you all take a look, now if you take a look, I would like you guys to circle. If you notice, you'll be able to see that the ester portion is the same between the two of them, right? Correct or not? They are the same. But the hydrocarbon section is different. And why is the hydrocarbon section different, guys? Because it will allow you to explain why vegetable oil is a what at room temperature. Thank you. Why margarine is a solid at room temperature. Now, if you take a look at your vegetable oil, it is made up of sp2 as well as sp3 carbons. Can you see that? And therefore, this is 120 degrees. This is 109.5 degrees, correct? Between 120 and 109.5, obviously, they are differing angles, right? So therefore, they cannot be packed very, very closely together. And therefore, the surface area of contact is lesser. And with a lesser surface area of contact, your London dispersion forces are weaker. And that's why the melting point is lower. And hence, it exists as a liquid at room temperature.
Wait, if you're more branched, shouldn't your surface area be greater?
No, if you're more branched, your surface area is more spherical.
Oh,
If it's more spherical, smaller surface area.
Okay, yeah, I understand.
Okay, if you're more straight, if you're not branch, more straight chain, then your surface area is more elongated, and if it's more elongated, the London dispersion forces are stronger. Okay, now
Why did you circle the 120
to show you that this one the bond angle is 120, this one here the bond angle is 109.5. Understand? Okay. Can Alright? Okay, now we shall start. I'm not going to go through this again because you already knew why is it called electrophilic addition. I'm just going to go straight into the mechanism itself. Now, mechanism is defined as chemical equation with arrows. Clear? Can So a chemical equation, you must balance your atoms, you must also balance your charges. Clear? Now, on top of doing both things, what else must you do? You must also show the movement of electrons. Now, a curly arrow that you look at like this, can you see the curly arrow? Represents the movement of electrons. And because it is a full-headed arrow, guys, alright, because it is 2 electrons, as you can see, so it is a full-headed arrow, right? Can you see? Therefore, it is the movement of how many electrons? 2 electrons. Understood? And then, right? Clear? So, what exactly happened is, let's do a bit of an analogy here by looking at these 2 molecules. So, what I'm going to do is, I'm going to assign each of us, alright, an atom. So, Kn will be carbon on the left, I'll be carbon on the right, X will be John, and Y will be Darren. Okay? So what exactly happens is this. I'm currently sharing 2 electrons with Kn. Alright, 2 pi electrons. So what exactly happens over here is, because I have 2 pi electrons over here, right? One of it is his and the other one is mine. Correct or not? So what I'm going to do is, since we were sharing, I'm going to take the 2 electrons and then pass it to John. Now when I pass it to John, guys, right? Kn's electron is now here. So because Kn's electron is here, Kn would have lost 1 electron, right? So Kn would have a positive charge. Understand? So this carbon atom on the left will have a positive charge. Agree? How about my charge, guys? Will my charge change or not? No, because my electron is still here. Can you see that? My electron is still intact. Now, John, however, which is the letter X, would have gained that 1 electron from Kn, right? So therefore, at this current moment, John's charge will be negative. Am I right, guys? Yes? Will be negative. So now, what exactly happens is, between X and Y, which is Darren, okay, John now transferred his electron over to Darren. Clear? So which means that we are now currently over here, between X and Y.
Wait, so the big arrow happens first?
The big arrow happens first, yes. Then after that comes the small arrow. So once he received that 1 electron from literally Kn, right? The 2 electrons now go over to Darren, in which one of the 2 electrons is originally his. You all agree, no? Because when you do a covalent bond, he contributed 1, John contributed the other. At the end of it, he received both. So what's the charge on Darren now? Is it -1 or -2? It's -1. Why -1? Why -1? Because one of it is already his. So he made a net profit of 1 electron, which is from John. Now, could you tell me what's the charge on John now? He was originally minus because he took Kn's electron. Now what is he? 0. He's neutral. I am neutral. You are what charge? Plus. So if you go over to this particular molecule, are you guys able to see the carbon plus is actually Kn? I am carbon neutral. That forms a dative covalent bond with X, while Darren is Y minus.
Why are you still SP2?
Sorry again?
Why are you still SP2?
Why am I SP2?
Why is the second C still SP2?
Because SP2 carbon is, because there's only 3 atoms around C+. There's only 3 sigma bonds, what? 3 sigma bonds is SP2 hybridized, what?
Yeah.
Do you all agree?
Yeah.
Can This is called a carbo-cation intermediate. Carbo comes from the root word carbon. Cation, which is a plus charge, intermediate. Guys, you all don't notice the plus charge, I put it on carbon on the right. Does it matter whether I put the plus charge on the right or on the left? Why not? Because the molecule is symmetrical. Are you all able to see? The molecule is symmetrical, that's why you can do this. And hence, this mechanism, this mechanism that where the plus charge doesn't matter where you put, applies for ethene, hex 3-ene, and but 2-ene. You all know what are these molecules or not? These are your symmetrical alkenes that are in your syllabus. Why did I stop at 6? Because your syllabus only deals with 6 carbons.
Because EN.
Electronegativity.
Wait. Can this not happen for like anti-fluorine though?
Huh?
Can
Can.
this not happen for? But then there won't be a difference in EN though.
But then the electron cloud of
But you'll still get polarized.
polarized, yeah. But not as much.
Yeah, okay.
Okay, now guys. So now we are at this stage. So the next step is when the Y minus, right, which is Diran holding the extra electron, correct or not? Now pass it back to Kn again. So if you notice how he does that, because of the fact that he is sp2 hybridized carbon, so he has an unhybridized p orbital, correct or not? And this unhybridized p orbital, okay, will accept the lone pair of electrons from Y minus. So therefore the lone pair goes into the empty p orbital of carbon. Understand, guys? So what type, can you see now, guys? The second step is actually addition of a nucleophile. Can see you're adding nucleophile?
Why nuclear?
Sorry?
Why nuclear?
Because Y minus is a nucleophile? But why do we call this electrophilic addition then when the second step is nucleophilic addition? Because the name of the mechanism is always based on the what step? Slow step. And that's the reason why we call it electrophilic addition, even though the second step is nucleophilic add. Hey, does it make sense or not to you guys?
Yeah.
Yes? Simple? Okay. Can Now let's move on to the next page, shall we? So, on the next page, you'll be able to see that this time round, we're not dealing with XY, we're dealing with XX, just like a halogen. Yes? Alright? So some of you might want to see how it polarizes the electron cloud. It's on the page here. Can you see the distortion of the electron cloud? Which induces a dipole, a delta plus and a delta minus. The one that did it is the alkene. Alkene approached the XX, it became this. Understand, guys?
Mm-hmm.
So, clear on this? So, when he's going to break up heterolytically as well. So let's take a look at how bromine breaks up heterolytically. So again, ethene, right? The 2 electrons that were shared between the two of us are now being given to bromine delta plus. Then the 2 electrons that were shared between the 2 bromine atoms is now given to just 1 bromine atom. So as a result, you get Br minus, agree? He is positive charge, and then the 2 of us are neutral. Clear? After the next step, what do we do, guys? We have Br minus, and the Br minus goes back and donates the lone pair of electrons into the carbon plus. Are you all clear on this? Now, you might be thinking, how come I put water here? Because the previous class did ask me, what's the difference between bromine in CCl4 solvent? What's the big deal? This is called liquid bromine. Means I take pure bromine, like concentrated, if you all drink Ribena, you know the concentrated Ribena. What do you all usually do with Ribena? You take a bit and then you add water, right? This is pure liquid bromine. You understand? Never dissolve in water at all. Clear? Now, aqueous bromine is you take the liquid bromine a bit and then you stir inside water. Agree not, guys? So when there's aqueous bromine, guys, aqueous comes from root word aqua, which is water, right? Agree? And water is also a nucleophile. So water competes with Br minus for carbon plus. So when you use aqueous bromine, you're gonna get two products, this and this. If you use liquid bromine, how many products are you gonna get? Just this, because there's no water to compete. So for those bio students, right, who takes bio here? None. Okay, good. So what they're trying to do is the two nucleophiles are competing for the carbon plus, and guess who wins, guys? Between water and Br minus. Water wins because water is the excess. Right? Clear? Okay. Are there any questions between the two? Is he back by?
I think tonight.
Oh, okay.
By Saturday.
Let's hope he comes.
You never know.
Yeah. Can? Okay, next is called electrophilic addition of hydrogen halide, which is represented as HX, correct guys? So instead of the alkene molecule polarizing HX, is now permanent dipole, delta plus and delta minus. Okay? So can you all read through the mechanism, see whether you all are comfortable before proceeding on to electrophilic addition or steam.
So the same thing, but
Same thing, but
already
it's already been polarized, yeah. These are not like XX, you know.
Wait, but for your hydrogen to take in your 2 electrons from the pi bond, it must have electric
What?
accessible orbital.
Orbital, yeah? It does, because he gave it away to bromine. He
So
gave his
everything is
electrons away.
simultaneous?
Yeah,
Oh.
concerted. Everything happens in one step.
So I gain it immediately.
I'll give a wave, yeah.
So the hydrogen takes an electron from the carbon and gives it to Br.
No. He takes the electron from carbon, full stop. And then his own electron, he gives it to Br. He doesn't take his electron and give it to Br. Get it? Yeah. Hey, okay not? What? Is it simple?
Yeah.
Sorry again?
No.
Hey guys, this one haven't covered in school, right?
No, not yet.
Okay. Have you all checked what topics are tested?
Everything.
Everything.
They give you
Prelims.
Yeah, everything.
August the 14th and
You
15th.
have the bromine, how do you get that?
Who gave you that?
Okay?
So
Alright.
all the same.
Same. It's the same thing, yes. Then the next thing that you all, so how many reactions have you learned thus far? Reaction with hydrogen, but it's not called electrophilic addition. Reaction with halogen, reaction with HX, and the last one is reaction with water. So there are a total of 4 chemical reactions in alkenes. There's a 5th one, guys. The 5th one is called addition polymerization, which you all did in bonding. But this is also covered inside this topic because for ACS, addition polymer is covered under the chapter of organic chem. Alright, guys, for electrophilic addition or steam, only industrial conditions, guys, only industrial conditions are what you all learned in secondary school. The laboratory conditions is brand new to you guys. Okay? Could you all now attempt exercise number 8 to see whether or not you are able to draw the following products? All good? Y'all know why aqueous bromine is Br and OH, right?
Wait, how does the OH come?
From water?
No, but how is it born? I thought OH then it will gain electron.
Huh?
No, your OH will be the one that gains electron.
Yeah. And
then that it will become negative.
who will become negative?
Wait, yeah,
Yeah.
makes sense. Makes sense, yeah.
I think I made him come on the stereo cam lesson.
What do you mean?
Faint lah. He wasn't around, right?
The
For
last one.
stereo cam.
Last week.
Yeah.
Yeah, it was on there. But isn't the lessons open?
No, there's one more. There's one class that they haven't. Abby's class, yeah, haven't done
Is it tomorrow?
Monday.
Next
The
week?
16, yeah.
Name come from listen. Not
Yeah.
watch the video.
I don't think he watched video.
Yeah,
Funny guy.
But the thing is, he will feel so out of place in that class.
yeah, no choice lah.
Right?
Yeah. Better than not watching the video also.
That's true. You actually watch?
Of course.
Wow.
See, I took all the notes.
On 1.5 speed?
No. Okay.
Oh!
What the?
You have this
That's
or not?
quite shocking.
No, I don't think
Okay.
so. Thank you.
To practice drawing Alkenes mechanism. Okay, I think I shall move on, yeah? Now, if you realize from the previous, I was only focusing on symmetrical alkenes. Ethene, butene, and hextriene, right? What happens if the alkene is asym? Correct or not? I mean, most of the alkenes are asym. The chances of you getting symmetrical alkenes is very, very low. So I want you all to take a look at your chem guide, okay? So that we are actually aware of what is really, really tested. So what is tested is, you need to be able to describe and explain the mechanisms for symmetrical alkenes, which I already mentioned to you guys. For halogen, steam, and hydrogen halide. You all know why I call it steam or not? Because if you check the temperature for addition of water, it is at 300 degrees Celsius. So that water will turn into steam already by then. Okay? So you need to know that you need to be able to draw mechanisms for this. Alright? Then you need to be able to predict and explain who is the majority product if there is a reaction between an unsymmetrical alkene and a hydrogen halide with water. Okay? So these are the two things that you all need to know. Alright, clear guys? For this chapter. Alright, so let's go back and move on to the next part. Then, this is called the stability of the carbocation, also known as Markovnikov rule.
Wait, but do you need to know how to draw an asymmetrical one also?
Mechanism, you mean? They can test, but they only testing symmetrical lah. But I feel that they can test for both lah. If you are allowed to predict the products, means you should be able to draw the mechanism as well. Okay? Now, take a look at the molecule. This is called but1-ene. Anybody disagree? The molecule here is called but1-ene. Is it sym or asym? Asym. Very good. So again, what I do is I separated the molecule into two sections. The right section is free radical sub. The left section is electrophilic addition. Okay? Clear? So now what we're going to do is we're going to add HBr. Alright? So HBr will be your H is delta plus, your Br is delta minus. Anybody disagree with me on that? Okay? So now what we're going to do is we're going to ask, because the first step is always addition of an electrophile. Correct or not, guys? So what we're going to do is we're going to add H to carbon labeled B, and we're going to add H to carbon labeled R, and you will get these two carbocations. Can you see the H added in pink?
Mm-hmm.
Are you able to see the two carbocations that are being formed? Yes, very good. So now, as you can see, the two carbocation ions are not identical like your symmetrical alkenes. Now we need to learn to classify our carbocation ions. So to do classification, we need our reference molecule. Our reference molecule is called a methyl carbocation ion. Now, I want you all to take a look. Your methyl carbocation ion is C+, right? And this C+ has how many H's around him?
3.
3 H's, very good. Can you see there are 3 H's around him? So your C+ has 3 H's around him. So take note of that. Now I want you to focus your C+ in the purple molecule. How many H's are there around C+? 2. Right? There are 2. Do you all agree? How many differences are there between the one in green and the one in purple? 1. So that's why it's called primary. Make sense? Now you go over to the molecule on the right hand side. If you go over to the molecule on the right hand side, you'll be able to see that there's only one H directly bonded to the C+. And we call this a secondary carbocation ion. Agree or disagree, guys? Agree, This is called a secondary carbocation ion. Now the next question will be, which one is more stable, correct or not, guys? Like which one will be, which carbocation ion is better? That's the main question that people will ask. Am I right? Is it the primary or is it the secondary? So what do you all think? Primary v secondary. Alright, you think primary? How about you?
Secondary.
Alright, secondary. So to answer the question, right, between primary and secondary, let's take a look at our methyl carbocation ion first. Now, let's talk about in general terms lah. Alright? When you have a positive charge fixed or concentrated on a single atom, the molecule, or in this case the molecular ion, will cease to exist. Why? Because this particular molecule cannot be stabilized by any of the hydrogen atoms. And why can't they be stabilized by any of the hydrogen atoms? Because the hydrogen atom is 1s orbital, correct or not? That's the electronic configuration of hydrogen, right? 1s. Agree not?
Mm-hmm.
Now, the issue here is that even though he is sp2 hybridized, so he possesses an unhybridized p orbital, this unhybridized p orbital cannot overlap sideways with a 1s orbital. Do you all agree? Because one is a dumbbell shape, 1s orbital is a sphere. So they cannot overlap sideways. Agree no?
Mm-hmm.
So therefore, there is no way, there's no chance, right, for the plus charge, for the burden, the plus charge to be spread around the hydrogen atoms. Are you all following? There's no chance in which you want to do that. So because of that reason, guys, this molecule, right, is highly unstable because the plus charge is only on one atom. We call it localized. Clear? So it's localized on one atom, making it very unstable. Now we move on to our primary as well as our secondary. We will take a look at a video of how the positive charges in these primary and secondary carbocation ions are actually dispersed or shared across the neighboring carbon atoms. Once the positive charge is being shared or dispersed across the carbon atoms, it makes the molecule very, very stable. Clear? And when it makes the molecule stable, guys, that there will be more of these molecules that will live to maturity. Make sense? And when they are able to survive, when a nucleophile comes in, the chances of the nucleophile reacting with either of them will be very, very high. Are you all clear? So let's say a secondary carbocation is more stable than primary. That means that his population size will be higher than a primary carbocation ion. Do you all agree not? And so because your secondary's population is higher than a primary carbocation ion, the second step involves the addition of a nucleophile. Agree not, guys? Mm-hmm. Right? The nucleophile will come in. The nucleophile higher chance will react as secondary one. Because higher population, chances of effective collision will be higher as well. So now what we're going to do is we're going to try to explain what they mean in this concept box. The greater the number of electron donating groups, the greater the extent of dispersal of positive charge. What do they mean by greater dispersal of positive charge? You'll understand? Clear? Can ah? So let's take a look at this video, is it? Okay. Okay, I'm just gonna go straight to this. Okay.
Unstable carbocation, which is the methyl carbocation. For this situation, what you need to understand is that this positive charge right here is localized to that carbon. This is what happens in a methyl carbocation. Now, what does that mean? Let me explain that. What we're going to see is that the fact that the positive charge is confined or localized to one area makes this thing less stable. And let me show you this by comparing our carbocation to a primary carbocation. Remember, that means there would be a carbon, at least one, directly connected to the carbocation. And let's move it over here and let's put the hydrogens that would be connected to the right carbon. So here it is, our primary carbocation, which we know is more stable than the methyl carbocation. If you were to determine the hybridization of the right carbon, you would get that he is sp3 hybridized, which, remember, that means he would have 4 sp3 orbitals about him, like this. Remember, these orbitals are overlapping with the s orbital of the hydrogens, and these orbitals are filled with electrons. But what I want you to focus on here is the fact that the empty p orbital would be parallel to one of the sp3 orbitals to the carbon on the right. And because of this, it means that they're able to make a connection to each other like this. And what that effectively does is help spread that positive charge or delocalize it so that the average positive charge would be right here between the two carbons.
So what he's trying to say is that when the p orbital of this carbon atom overlaps sideways with one of the sp3 hybrid orbitals, guys, what exactly happens is he forms a pi bond right here. So the 2 electrons that was between carbon and hydrogen will now be able to spread and neutralize the positive charge that's on the carbon atom. And when that happens, you can see that the positive charge has been averaged out across the 2 of them. And when the burden of the positive charge has been spread out, that makes the molecule a lot more stable. Are you all clear? So this is why they say that the primary carbocation is more stable than his predecessor, which is the methyl carbocation, the reference carbocation that I was showing you guys. Okay?
These orbitals connecting to each other is called hyperconjugation. The fact that
This term don't need to learn, huh? Hyperconjugation, you don't need to learn. Alright?
these orbitals are able to hyperconjugate means, again, that that positive charge is not going to be localized. That's one way to think about it. But here's a better way, I think, to think about it. Remember, it's the sp3 orbital on the right that has electrons in it, and it's the p orbital on the left that's empty. That means once these two orbitals hyperconjugate, the electrons in the sp3 orbital can now move towards the empty p orbital. And spreading out electrons decreases the energy of the molecule because, remember, electrons want to repel each other. So the fact that these two orbitals can hyperconjugate means that it allows the electrons to spread away from each other. That is almost equivalent to saying that positive charge is also spread out as well. Notice we wouldn't get hyperconjugation with a methyl carbocation. There's simply no carbon next door that bears sp3 hybridized orbitals. And notice the many ways in this case that this molecule can hyperconjugate. It could hyperconjugate with this bond like we saw in the example. It could also hyperconjugate with this one or even this one. And think about it, it makes sense. The more chances to hyperconjugate, the more we have the ability to stabilize the carbocation next door. So let's take this concept a little farther now. Let's say we connect 3 carbons directly to our carbocation. Remember, that would make this a tertiary carbocation. And let's just focus on each hydrogen connected to these carbons right here. Think about all the chances to hyperconjugate in this case. In this case, you can have either one of these bonds hyperconjugate with that central carbon. And remember, in doing so, we have what's called an electron donating effect. And that is, remember, each electron in the CH bond is able to donate towards the empty p orbital like this. And think about this as well. Each one of those carbons directly connected to the carbocation has two other additional hydrogens connected to it. So that gives us even more chances to hyperconjugate. So that's why we observe this trend. It simply means that the tertiary carbocation is the most stable because he has the greater ability to hyperconjugate. So what are our key points here?
Okay, Ken?
Like if you go back to the CH3, right?
Yeah.
If you donate an electron from the CH to the central, then the CH1 is gone. Because they only have...
Yeah, but the electrons are constantly moving up and down.
Oh.
It's not they donate. The electrons are just moving further. They won't be localized between C and H.
Like
it will not be delocalized.
It's like the benzene.
Correct, it's like the benzene ring. So the chances of these two electrons meeting each other will be lower. And when they meet them, when the chances of meeting them is lower, that translates to more stability, because inter-electronic repulsion is minimized. Understand? So if you take a look at the screen again, guys, are you guys able to see? The greater the number of electron donating alkyl groups, the greater the extent of dispersal of the positive charge on the carbocation. Okay? And the greater the stability of the carbocation form. Can? Alright? So, I mean, in conclusion,
So your
tertiary will be the most stable, followed by secondary, followed by primary, and then the last one will be methyl. But methyl doesn't really exist lah. Okay? Now, this is basically Markovnikov rule. So guys, every single mechanism that has every single mechanism that eventually leads to every single mechanism that involves a carbocation that is being formed has Markovnikov rule. So in 2 chapters time, which is next week for you guys, you will learn about halogen derivatives, and you will see a carbocation that is being formed again, and then it is your job to be able to explain why this carbocation is more stable than this carbocation. Clear? So if you take a look at this example here, you have an asym alkene, and you are adding an electrophile as well as a nucleophile. Correct not? An electrophile as well as a nucleophile here. Can? And you produce 2 differing carbocations, a tertiary carbocation as well as a secondary carbocation. Could you please label it as less stable as compared to your tertiary carbocation?
asymchus is 3 R's and 1
Yeah.
H.
Can I? So, as I mentioned, the major product will be the product with the highest quantity or the highest yield. Understand, guys? Okay, let's carry on to the next part. So, if you take a look at exercise 9, yeah? Okay, if you take a look at exercise 9, you are dealing with an asym alkene, correct or not? And how do we do it very, very quickly without even drawing the carbocations? Because if you take a look at your chem guide, they said, explain the major product for a reaction between asym alkene and a hydrogen halide, right? So, if you go over here, this is an asym alkene and this is a halide. Agree or not, guys? So what you can do is to do it quickly, guys. So listen up. This is a carbon-carbon double bond. The doubly bonded carbon on the left has only 1 hydrogen that is directly bonded to him. The doubly bonded carbon on the right has 2 hydrogen atoms that is directly bonded to him. Are you able to see that? Now I'm going to get ICl. The I will be the electrophile, while Cl will be the nucleophile. Agree? Correct? So one is electrophilic, the other one is nucleophilic. So the iodine will go to the side with more hydrogen atoms. So if you notice, if you take a look at your product, can you see that the iodine or the electrophile will go to the side with more hydrogens? And this is where the nucleophile will end up. Can? So this is how you do it quickly. You label the number of hydrogen atoms on each doubly bonded carbon atom. Then the one that has the more hydrogen atoms will receive the electrophile, while the one that is lesser in hydrogen atoms will receive the nucleophile. Clear not? Yes?
Wait, this one. The one that has more
Hydrogens will receive the electrophile,
the electrophile.
while the one that has lesser hydrogen atoms will receive the nucleophile.
So this just grew or like why is that happen?
Because of the carbocat ion?
Oh,
But you don't want to draw the carbocat ion because we want the answer to be out quickly. What?
Yeah, okay.
So what we do is we go over to the alkene molecule, we check who has more hydrogens. The one that has more hydrogens attached to the doubly bonded carbon atom will receive the electrophile, while the nucleophile will be received by the one that has lesser hydrogen atoms. Can?
But it's just probability, right? It can happen the other way also.
Yeah, but the one that follows this will be the major product. Now, if you cannot see this pattern, then I suggest for you to draw carbocat ions for both and then label the carbocat ions secondary versus primary. Can? After that, then you select. Okay? Are you all clear on this?
It has not been
like everything for
What does that look like? There was one playing Smash.
Huh?
Just play Smash already, no stop.
no I played during the break.
Not break, study break.
Yeah.
The break longer than study, yeah, actually study.
Huh?
Plus your breaks are longer than actually study.
Yes.
I don't study break.
I do. Actually I did physics. The atomic
Time dilation.
No, but that one's not jet.
Need bro.
It's too difficult.
Well, I'm telling you, exam will come out, there's 20 marks.
The final
I'm
question.
time travel.
Is it possible to time travel? Is it no?
You're right, I say 20 marks. Okay, I'm not now. Okay, no one now. Okay, turn off.
Go on,
No, turn off.
okay.
There's stats, normal, or like zero stats.
Zero.
No, I see.
Wait, no stats means
Means
everything
like-
max or
No, means we are both levels, everything
it
is
is some
zero.
shit bro.
Let me jump in stats.
Yeah.
I'll really stats.
No dude, the stats it don't matter that much.
Okay. Actually, yeah, it's minimal.
It's not the whole story.
It's minimal. Are you on? Let me create. Try.
It's what? 6.
7. Not so low. Lag. Relax.
Dude, I mean like serving's a disadvantage. You can't lie.
Yeah, actually is.
Okay. So the next question that some of your peers did ask me a few days ago was whether or not this compound is optically active, because he saw that there's a chiral carbon here. Can you see the chiral carbon or not? sp3 carbon bonded to 4 differing groups. Agree?
Yeah.
Unfortunately, being chiral is only one of 3 criteria for you to be optically active. The other 2 being you cannot have an internal plane of symmetry, and you cannot be in a racemic mixture. Do you still remember racemic mixture? A racemic mixture is when you have 50% of each enantiomer. Correct? So guys, why is this optically inactive? Is because of the carbocation. The carbocation, guys, is flat, you see. Correct? It is flat like this. So now, because it is flat, you have an unhybridized p orbital, and the lone pair of electrons from Cl minus can be donated from the top or can be donated from the bottom in equal probability, right? So if it's donated from the top, that basically means that you are going to produce one enantiomer. If it's donated from the bottom, you're going to produce the other enantiomer. Understand? Clear on this? So therefore, because there's an equal probability of producing either enantiomers, that means that you're going to get a racemic mixture. And hence, even though you have a chiral center, you are optically inactive. Alright? Now, I want you all to take a look at the answering technique because of the fact that this is part of your chem guide. You need to be able to explain the major product. Can you see that? So the explanation is right here. This is the explanation. Whatever the carbocation that you have chosen, because it has greater electron donating effect, that was seen from the video, and therefore you will have a greater extent of dispersal of the positive charge on the carbocation, which means now the positive charge is averaged out, and hence your carbocation is more stable. And when your carbocation is more stable, the population size of the carbocation will be a lot more, and because it's a lot more, that translates to a higher yield.
So carbon with less hydrogen would be a major product.
Less hydrogen attached to the carbocation. Can Okay, could you all attempt question number 2? Alright, but before that guys, this one addition polymer was covered in bonding. So okay, you all please go read up on bonding, yeah? This one actually nothing much, it's exactly the same as secondary school polymer. Nothing changed. And the last part, which is on the preparation of alkenes, alright, this one is not in syllabus lah. Okay, can? Via the elimination reaction. All this Zaitsev rule is not. So the next time when I see you all again, which is on Saturday, will be on page 56. Alright? So could you all now attempt 2A, B and C? After that, we have to move on to these worksheets. You all have this read? Not yet, right? 3, 4, 5. Can? Okay, do question 2 first.
tell me, bro.
Mm-hmm.